So we've been looking at typing rules and type environments, and we also looked at how type environment is used to resolve the type of a variable and how type environment can change as you are walking the abstract syntax tree. Our next topic is about typing of functions or methods. And consider a function call like the one shown here. So let's say f is a function or method, and it is being called on n arguments. Each of the arguments is an expression, let's say e1, e2 and up to en. And we're interested in finding the type of this particular expression. So this call of a function, or also called a dispatch of a function for certain actual values of arguments, basically evaluates to an expression, which is probably the return value of the called function. And so we assume that we already know the types of e1, e2, en, and that would form our hypotheses. So for example, the hypothesis could say that e1 is of type t1, e2 is of type t2 under a particular type environment. And notice that we're using the same type environment because we're basically assuming that the type environment is not changing during this function called dispatch. Now, en is of type tn, and then f needs some type as well, and based on that we will be able to say what is the type of this expression f applied on e1, e2, en. Now there are two things that are missing here. One is how should I represent the type of f, and the second thing is, even if I know the type of f, how do I know what should be the type of this dispatch or this call to the function? And I need a rule that is both sound and precise. All right. So here is the answer to the first question. I'm going to represent the type of a method or a function f as a tuple t1, t2, tn and tn plus 1 to represent the fact that f can take n arguments of each of type t1, t2, tn, and if it gets these arguments of these types, then it returns a value of type tn plus 1. So this tuple basically represents that the first n types represent the types of the arguments, and the last type, which is tn plus 1, represents the type of the return value. Okay, notice that these types here are the formal, these types are for the formal arguments x1, x2, xn, and these can be replaced by the actual arguments during a function called dispatch. Alright, so now that we have a type for f, so now let's revisit our function called dispatch typing rule. So under a type environment O, E1 has type T1, E2 has type T2, En has type Tn for some types T1 to Tn. F has types T1 prime, T2 prime, Tn prime. Notice that T1 prime is different from T1 and so on. And Tn plus 1. Notice that Tn is primed, but Tn plus 1 is not primed. And it is true that T1 is a subtype of T1 prime, T2 is a subtype of T2 prime, and so on till Tn is a subtype of Tn prime. Then I can say that the dispatch f of e1, e2, en is of type Tn plus 1. So let's look at what's happening here. Basically, I'm saying that if f accepts arguments of type t1, tn and returns a value of type tn plus 1, then, and if e1 is of type t1, tn, but I have a twist here. I'm saying that e1 and e1, do not need to be the same type as the types of the formal arguments. They can be subtypes of those formal arguments types, right? So e1, e2, en represent actual arguments, and so the actual arguments can be a subtype, can have a type as a subtype of the type of the formal arguments. So that's what it represents. So e1 has type t1, and t1 can be a subtype of t1 prime. T1 prime is the type of the first formal argument. And so, this is to make the rule more precise. I could have just used t1 instead of t1 prime here as well, but that would not be as general, and that would reject many programs, many correct programs. So I want to be as precise as possible, and so I'm accepting any subtypes as arguments of the formal, any subtypes of the formal arguments as the actual arguments, and in that case I'm going to return a return value of tn plus 1. Okay, so once again I want to point out that if T1 is a subtype of T1 prime, then E1 can be used in place of the first formal argument, which has type T1 prime, and recall that E1 has type T1. And notice that the return type is just Tn plus 1, so there is no primed version of the return type, because there is no meaning of primed version in this particular setting. Alright, so that was a function called dispatch for any general function, but let's also look at the special case where the function is actually a member function of a class. So let's say it's an object-oriented language, and I want to define this function as a member function of a particular class. So in which case, let's say there's a class C, and then this represents a declaration of a function foo. It has some return value, return type. This is the name of the function, and then these are all the formal arguments of this function. So for example, the type of A1 and then A1, type of A2, A2, and so on till type of AN, AN. And let's say at some point in the program, I basically instantiate a object C, small c, of the class capital C, and then I dispatch a call to foo on the object C, small c, right? So the difference between this dispatch and the dispatch that we saw on the previous slide is that this is the object-oriented version of the dispatch, because foo is a member function of class C, and small c is an object on which foo is being, from which foo is being resolved. Right? Notice that small c could have been, in this case, in this particular example, I'm showing that small c is an object of type capital C, but it is also possible in an object-oriented language to instead have this to be a small an object of type capital D, such that capital D is a subtype of C. All right. In which case, also it would be okay to call foo on C, because small c is an object of type D, which is a subtype of class C, and so and C has foo, so it's okay to say C dot foo in that case as well. And so the first thing I want to do is basically correctly identify which foo it is, because maybe foo is so I want to know where was foo defined, or in which class was it defined. Was it defined in C? Was it defined in D? Was it defined in some super type of C or something like that? So to do that, I'm just going to have this annotation. So whenever I say C dot foo, I'm using our scoping rules. We will basically know that what is this foo, where is this foo coming from, what is the declaration that matches with this particular identifier, and using scoping we'll be able to resolve this. And I'm going to instead say C, qualify it precisely to say small c at capital C, so dot foo, which basically means I'm calling capital C's foo, right? So it's completely disambiguating that foo is a member of class capital C, because it could have been a member of any particular class which is present in the type hierarchy. Alright, so with that disambiguation, now I want to have a rule, a typing rule, and say how do I resolve whether this expression is correctly typed or not, and if it is correctly typed, what is the type of the return value. Okay, so here is the member function dispatch typing rule. It looks very similar to the rule that we had for a general function dispatch, non-member function dispatch. So E0 is a type T0 under an environment O, and so on. And then instead of f, I'm saying t dot f. So t dot f represents that f is a function of some arbitrary class capital T. And then I have, just like I had for function dispatch, I have a type signature for t dot f, which is again t1 prime, t2 prime, tn prime, and tn plus 1. Basically meaning that it takes n arguments of types t1, t2, t1 prime, t2 prime, tn prime, and returns a return value of type tn plus 1. Now, so basically it's going to look very similar, that I'm going to say that, so apart from E is 1, so last time we just had E1 dot En, but now I also introduced an expression called E0, and that E0 would form the expression object on which f is being invoked, right? Recall that a member function is invoked on an object of a given class. So I'm going to say E0 at t dot f. This represents that the value of the object is represented by the expression E0, and at t basically at t dot f represents that I'm interested in the f present inside class t, and capital T should be a super type of the type of E0, hopefully, for this to be well typed. And so we're going to have that in our hypotheses. And then E1 dot En, those are the actual arguments, and then what should be the type. All right, so here is the full rule. If T0 is a subtype of T, so basically notice that I have E0 at T dot f, so this can only be well typed if the type of E0 was a subtype of capital T, so it was derived from capital T, and so that's what this particular hypothesis is stating. T0 needs to be a subtype of capital T. Similarly, just like our regular function dispatch, the types of E1 dot En need to be subtypes of T1 prime, T2 prime dot Tn prime respectively. So T1 needs to be a subtype of T1 prime, T2 needs to be a subtype of T2 prime, and so on. Tn needs to be a subtype of Tn prime. And if all these hypotheses or conditions are satisfied, then under the same environment O, E0 at T dot f E1 dot En has type Tn plus 1. So this is the type rule for our member function dispatch. And this is also a sound type rule because the type returned matches with the value that would be computed at runtime. It is also a precise type rule because we are trying to be as general as possible in accommodating all possible correct programs by using the subtyping relation. Okay. I want to kind of discuss the notion of function polymorphism that's present in many languages, including C and C++. For example, the same identifier foo may have multiple signatures. So for example, in this case, foo takes an integer argument and returns an integer return value. And yet another function with the same name foo takes a long argument and returns a long return value, or a string argument and returns a string return value. Now, the first thing about this type of polymorphism is that if there are multiple definitions of the same identifier foo with different arguments, that is acceptable. But notice that in this case, in the fourth case, I have foo that takes integer but returns a string. Now, this would be incorrect because I already have a definition where foo takes an integer argument and return int, and here foo takes the same integer argument but returns string. So different versions of the same identifier are possible, but they need to have different arguments because otherwise there is no way for the compiler to identify which foo to use, right? I can only look at the arguments to decide which foo to use. And so this kind of usage, this kind of polymorphism is incorrect. So I'm not going to consider this because languages typically won't support it, because here it's the same set of arguments but a different return value. So that's not legal. But this type of polymorphism is possible to support, and it's easy to support actually. And the way to do this is simply maintain multiple type signatures for an identifier inside the type environment O. So, I have, for the same identifier foo, I could have int to int, long to long, or string to string. And then when I'm actually doing type resolution, then I can check what is the type of my argument. And depending on what's the type of the argument, I will know which foo to use, right? So for example, if the type of the argument is a subtype of string, then I would use the third foo. If it's a subtype of int, then I would use the first foo, and so on. Now, even there may be a chance of ambiguity. For example, if I just say 1 or something like that, then what is it? Is it a long or is it an int? If the actual argument was just an integer constant, it could be a long or an int. Where different languages could take different approaches. For example, they could throw an ambiguity error saying that, look, I couldn't figure out which foo are you talking about. Or they could have resolution rules or precedence rules where they could say that, I'm going to maybe look at the one that matches most precisely, right? Or I'm going to look at the first definition of foo in case of multiple matches or something like that. Now that is just a language design decision, and different languages could take different approaches there. All right. The other thing to notice here is that while I've been talking about expressions as though they are appearing in a free form outside of all the classes, often in object-oriented languages, expressions are being used or defined or specified inside of class definitions or inside of the body of the member functions of the classes, right? So for example, the body of a member function, in which case I may need class-specific environment while dealing with an expression. So for example, the C++ programming language has the notion of a this keyword. Now what should this resolve to? What should be the type of this? Right? It really depends on what is the current class in which this is being used. And so the type of this would be the context of the current class in which this was used. And similarly, I could access member variables or functions for that particular class if I'm in that particular class environment. And notice that our type environment, which is O, does not really capture the notion of what is the current class. It just has a mapping from identifiers to their types, but it doesn't capture what is the context in terms of whether I'm inside a particular class or not. And so with just using a type environment, I won't be able to resolve the this keyword, for example. And so it's easy to solve something like this. We just need to extend the environment, right? And so anytime we basically want more information from the environment, we need to extend the environment, and and in this case, we need to know the current class in which the expression is sitting. And we will change the form of our sentence or judgment, typing judgment. And earlier it was just under the assumptions created by the type environment O, it is true that E has type T. Now I'm going to say under the assumptions of type environment O, and if I am sitting in the current class C, or if my current class is C, then E has type T. So for example, I could have a rule which says that O, C, this is of type C star, right? So basically this means that if I am currently if my current class is C, and I ever see this expression called this keyword in C, then its type is going to be a pointer to the current class, which is C star. Okay, so this is how I am going to change the form of my sentence, and all my current rules that I had, typing rules, I can just add C to the left hand side of the turnstile operator. Just like when I added O, now I can add more environment variables. In this case, it's the current class C. So for example, I could change my add example to O, C. Under O, C, E1 has type int and E2 has type int. Then under the same O, C, E1 plus E2 would have type int. Alright, so here's a summary of typing rules. Type rules are defined on the expression structure. So notice that in all the typing rules, we are looking at one particular operator that is possible in an expression tree, and so we have already discussed how the type proof basically has the same structure as the abstract syntax tree, one for each node of the abstract syntax tree. So the type rules are defined on the expression structure. Types of identifiers are modeled by an environment, for example, O. We also said that types of certain things may also depend on the current class, and so some identifiers, for example, member functions or member variables, may depend on the environment C as well. Now, just a word of caution: type rules are very compact. They have, very dense notation, and so one has to be very careful about reading the subtle details. For example, T1 prime and T1, Tn plus 1, and so on. I mean, they encode a lot of information. For example, when I say that I'm using the same identifier or same environment O at different places, I'm basically implicitly implying that I'm under the same environment. All right. So while being compact is a good thing because it makes things easy. It makes things shorter and more easy to kind of communicate because they become more shorter. They also require more effort to read, and so that's something one has to be careful about.